All right, students, welcome into week 7. We didn't have a class last week. I apologize. I was, put on a list to get a COVID vaccine, and I could not pass up that opportunity. But it worked out pretty well because that was just night 2 of like a 2-part module. And so we are back in the swing of things for week 7. Please make sure you're keeping up on CK12. Please make sure you're keeping up on the discussion boards. You can see on here as you are looking at my screen. A lot of people are starting to get their discussion boards done, which is good. You don't want those to get too far behind. And same with the CK12 work. There's still a lot of people who haven't really gotten into that and started going. You're setting yourselves up for a very, very hard time at the end of the course. So let's just go over this week's stuff. So we're getting into, if we take a look at what we've done so far, we looked at Earth's place in the universe. Then we looked at our Earth, Moon, Sun system. Now we've looked at the layers of the Earth, how it's constructed, and now we want to know what the Earth is made up of. And so for that, we get to jump into rocks and minerals, which is one of my favorite topics and subjects. I double majored at Cal Poly Pomona. I did geology and geochemistry. The chemistry ties into geology so beautifully and wonderfully. The two are just inextricably linked. And so it's fun to talk about rocks and minerals. We'll dab a little bit of chemistry in there, not much, just more informational purpose. And then, we'll really get into it. I have a couple of my personal minerals here that I have collected over the years. Yep, I'm that dude. I got a mineral collection. And to the point, it's not just, I got a shelf full of rocks. I got storage facilities full of rocks and minerals. I have more rocks and minerals up than I have pictures of my family. I'm not joking. I have more insurance on my mineral collection than I do on my car. That's the level of awkward, weird nerdiness that I have sunken down into. But anyway, it brings me joy, so don't judge me. I like it. It's fun. It's been collected over my years of taking geology courses, going on geology field trips, and just my own rock hounding, which is a lot of fun. So let's hop into this week. So we have our typical course here on Canvas. So I'm going to click on our course. It's going to take us to our familiar page. All the info you could ever want to need. You're probably sick of seeing it. A rubric for how things are graded here. And then here's our modules. And let me move this guy out of the way. So we are now in Module 7. So if you click on here, you're going to see the familiar format that you always see. So just like always, we start with our discussion board, a link to our CK12 work. And actually, no, let me rearrange this. I meant to do this earlier. I'll rearrange that, and I'll rearrange those too. So we'll put CK12 work at the bottom because we should really be focusing on the lecture before we go to the CK12 work to get that added information. And one thing I will say with this week's presentation, I've included questions from the quiz on the PowerPoint. So as long as you're listening to the presentation, you'll have 3 free answers on the quiz. It's not too shabby. So let's start with the discussion board. So if you click on that, it'll take us right to our discussion board. Notice on this one, there is no video. There's simply 3 questions with associated links. And so what you're going to do on this one, we just want to start talking about minerals because minerals are the building blocks of rocks. And, a rock is just an aggregate of minerals. So we want to start talking about minerals first before we jump into rocks. And this will also help us when we get to plate tectonics and other topics. I'm sorry, there was just a noise out in my backyard. My dog looked over, I looked over. It was intense. It was scary. I'm joking. Anywho, so so the first question is, I like to throw these in there. I know they're not super scientific or they don't relate to anything, but anytime that they classify something by month, I'm all about it. I love it. Like with the full moons, which we are about to have our February full moon, probably tomorrow when we have our class. Let's see. 2 days. So the 26th, so Friday. Friday will be the full moon, which is that February snow moon, which is awesome. But anyway, so this one is just the stone for your birth month. So this is February. So amethyst. Amethyst is the stone for the birth month. So you're just going to look at this list. You're going to find your birthstone and you're going to pop it right on there. And then for the next question, you're going to be looking at some minerals that fluoresce. So that link is going to take you out to talk about fluorescent minerals. And you're going to look through, just follow the instructions on there. You're going to tell me the name of the mineral. Like there's a whole list of them, and they show them in black light so you can really see how they fluoresce. And you're just going to pick one out. You're going to tell me the name, and you're going to tell me where it's found, because I always have the occurrences on there. And then you're going to pick one more piece of information about that mineral. It could be its chemical composition. It could be what rock it's found in. It could be the mineral or the chemical that makes it fluoresce. Your choice. But just learn a little bit about it, because it's kind of cool. And then the last one, it's going to take you to a page that has a link for a bunch of minerals. And then what you're going to do once you get to that link, you're going to pick one. It could be any one of these. So look at all these you have to choose from. You know, there's no shortage of options there. And you're going to click on one. So let's say if I went with, I don't know, feldspar. That's a super boring one. This comes up. Don't bother. Click out of that. We don't need ads here. But so feldspar, it's one of the most common minerals. I shouldn't call it boring. It's not boring. One of my favorite minerals is amazonite, which if you look that up, A-M-A-N, A-M-A-Z-O-N-I-T-E. So amazonite. And it's this really cool, like a greenish rock. And it is a feldspar, but it just has lead as part of its chemical composition, which gives it a cool green color. Let me get rid of some of this advertising. I don't need chandeliers. Get out of here, Lamp Plus, unless you're going to sponsor me. So if you start hearing me say, this lecture is sponsored by Lamps Plus, yeah, if they're not going to pay me, I ain't going to advertise. That's just the way it goes. But anyway, so you're going to get this plethora of information about feldspar, and it's really cool, useful information. Feldspar, this thing right here, it's in your toothpaste. Weird. But you can keep reading on and sort of understand why that is the case. And it has a lot to do with what we'll talk about later on. But so what you're going to do, so that's going to give you all this information. And so you're going to pick one out. You're going to tell me the name of the mineral you choose and its chemical classification. So if I scroll down here, a lot of information here. But on the right side, it's going to tell us, our chemical classifications. Oops, actually, this might not be the best one to have chosen. Let's see. Okay, mineral classification. There we go. So you're going to get in there. I was really hoping it would just show us the silicate one in there. But let's see. This one doesn't have the same setup. So let me show you what I was talking about with some of the other ones. So I just want these to be as easy for you as possible. So if we go with diamond, here's a nice one, diamond, right? So you get all the information, and when you look down here, chemical classification. So it's a native element. So that is technically its chemical classification. It's a native element, which means it's pure. It's only carbon the whole way through, as opposed to if you hopped to another one. Let's see. Spinel is a fun one. I like spinel. Look at that. Look how pretty that is. But if we go down here, look at that. Oh, talk about some serious bling. Oh, my goodness. Anyway, so if we go down there, chemical classification, it's an oxide. Right on. That's cool. And then after done with that, I'm also going to ask you, where is it found? What's its occurrence? And so as you scroll down through all of this will be talking about, so the spinel group, it'll tell you about where it's found, maybe even the specific mine where some of these came from. So I just want the location, like where it's found, the geological occurrence, and the chemical classification. So just tell me where it's found and tell me what chemical classification it is. And that's it. So that's pretty cool, pretty simple little discussion board there. No video to watch. Trust me, I looked up all the videos on rocks and minerals, and even the ones that were 2 minutes long were incredibly boring, and it's only 2 minutes. So, I wasn't going to do that to you. But anyway, so let's hop back to our module here. And so that's our first part. Please make sure you're doing it. It's 10% of your grade. It's a full letter grade, and it's just the easiest way to get 10%. So let me hop now. Let's just take a look at our CK12 work as we fly over there. So let's look at it. So as we log into it, if I go to the classes, just to keep you updated on some things, when we go to Earth Science, when I scroll down here, if I go to assignments, oops, nope, let me go back to the home of the thing. Where's my little, there we go. Go back to assignments. Oh, wait, no, I blew past it. I'm so sorry. Just give me a minute here. Part of me wonders, so I know a couple of you watch these things. So when I mess up, I'm like, oh, it doesn't matter. They're not watching anyway. No, but I hope you are. For goodness sakes, please do. So from the start of our class here, so we got 22 people done with this assignment. Awesome. And as we go forward, it starts to go down a little bit more. And then this is the concerning part. 6 people have done Earth's interior. You had 2 weeks. 2 weeks to do Earth's interior. Not good. Especially like if you haven't started at all, you have to get a little concerned about being dropped. Just because if you haven't done anything thus far, I don't even know if you're part of the class and participating. And so just keep that in mind. Don't get too far behind on this. Like you had 2 weeks on it. A lot of this should be done. And hopefully you get started on it. That actually, now that I see it, it's pretty worrisome. But you make your own choices here. I make it easy and available. If you choose to do it or choose not to do it, that is up to you. So you're going to watch me in action here, make your assignment available. It is rocks and minerals. You can get a preview of what we're looking at next time. But so I'm going to assign this to you right now, and the due date is going to be a week from today. And now it has been assigned. So if we go back in here, so this will be due the first week of March, and so you'll find it under the March part. And so I'm going to go to rocks and minerals, and you can see here, you got 5 sections, 1, 2, 3, 4, 5. And then for some reason, the title of the quiz didn't pop up, but this is your quiz right here. So same as before, you're going to click on each of these sections. It's going to bring up articles for you to read. It's going to bring up videos for you to watch, which usually pertain to the questions that are being asked in the adaptive practice. There's activities you could do to help you sort of develop that deeper level of understanding. And then also there's study aids for when you're doing the adaptive practice or the quiz. You can use it for that too. And then real world examples. The real world examples in this section is going to be very, very important because, with rocks and minerals, we have a gazillion real world examples, and they help to clarify it. Because one of the hard things with minerals is we have to start thinking in 3D, and that's not an easy thing to do. I know, like, you may have tons of experience with, movies and 3D, but to think in 3D, how things grow in 3D is actually kind of difficult. But so just as before, so you know the sort of routine of it now. You go through each of these sections, you do all that, you get to the quiz. This quiz, 22 questions. It's a little bit longer, but it's not too bad at all. And so let's hop into the meat of the lecture here. So going back, I'm going to hop back pretty much. So this is going to be the PowerPoint with no lecture. So you're going to see that here. And this is what we're going to do. And then the other one that says, actually, let me hop back. So I'm going to get to this in just a second. But this one that says lecture and PowerPoint, that's going to be what you're watching right now. I don't know why I'd hop back to that. It's not even there anymore. But you can click on that and you can watch this as many times as you like. Bump up my views. I don't know. So anyway, let's talk about rocks and minerals. So I'm going to extend this and we're going to start to talk about it. Hopefully, we can get through it a good amount of time, but it is very important for us to go through. So rocks and minerals and rocks, they are all around us. You go walking, you go for a hike, you're walking, right by rocks, which are made up of minerals, or you can find the individual minerals lying around. And so, hey, go to the next one. There we go. All right, so we want to look at what are minerals, what are some of the common rock-forming minerals, how are minerals sort of classified based off of their physical properties, the basic rock types, and then we want to look at the rock cycle as we hop into it. So with minerals, a mineral is a naturally occurring solid crystalline substance, generally inorganic, with a specific chemical composition. So let's break that down. Naturally occurring, so it has to occur in nature. It can't be artificially made. It is not qualified as a mineral in that case. A solid crystalline substance, so there has to be an orderly crystal arrangement. And then generally inorganic, meaning that it's not coming from living things. The exception to this is coal. Coal is a mineral, but it is from dead plant and animal material. So that is one of our few exceptions with that clause. And then it has to have a specific chemical composition, meaning if I had a chunk of, I was talking about, let's see, spinel. If I had a chunk of spinel and I did the chemical composition and I broke it up, that chunk would still have the same chemical composition. If I broke it down, it would still have the same chemical composition throughout. All right, so it has to be natural, like we said. It is a solid, and then the atoms are arranged in an orderly repeating 3D array, which is called a crystal. So there we go, there's your crystal right there. So not part of the tissue of an organism. So the coal being like plants and animals, it is not their tissue. It is, the harder parts of it, like the shells, or when it comes to plants, it could be like the structure of the plant, and they don't really have tissue anyway. So the composition is fixed, or it could vary within defined limits. Some minerals will have more of a substance than another, but generally it's the same composition. And then so minerals, they are the building blocks of rocks. So if you look at like a common rock, like a granite, you notice the different colors and the different things, and they are all minerals. So just those different aggregates of minerals put together, we have ourselves a rock. So let me try and move this little guy out of the way here. Let me hide it. I hide this. Perfect. Okay, so with minerals, so we have large individual crystals being very rare. And the reason that's rare because they need room to grow. If they don't have room to grow, they can't get very big. So depending on the space that they have to grow is what's going to determine the size of the mineral that can grow. And so usually it's a mass of small grains, but each of those grains is a crystal. But grown up against each other, that's why some of them can get deformed. That's why they don't always look the same, because they're kind of like buttoned up against one another. This crystal of quartz right here, perfect example. This one clearly had a bunch of space to grow, and so it grew huge. These ones down here kind of like bumping into one another. Maybe they couldn't like fully mature, kind of like bullied around, all that stuff. And, speaking of quartz, I'm going to show you one of my samples right here. And this is a big sucker. Look at this. This is hand collected. This is my baby. I'm joking. But no, this is one of my favorite minerals collected just because of its size. But then also, if you look at it, it has that almost same crystalline structure that we see up here. So any crystal of quartz, given enough space, is going to look as such, kind of like a little spear. All right, so let's put that one to the side. There's your first example. So the atomic structure of minerals, if we take halite, which is sodium chloride. So this right here, this is your table salt. So if you're watching this right now and you're like snacking on some food and you like poured some salt on there, you just pour minerals onto your food, dude. Like, that's kind of cool. If we were deeper into a chemistry class, like I would tell you how cool it is, because sodium Na in that formula is a highly reactive metal. It's an explosive metal. It's a contact explosive. And chlorine on its own is a poisonous gas. But you combine those two together, highly reactive metal, a poisonous gas comes together into something delicious. Once again, knowledge is delicious, literally in this case. But so in our halite crystal, we have these sodium chloride arrangements, if you will, that are these nice, perfect cubic structures. And so you can see how the sodium ion, as part of the NaCl format, fits in and like in this perfect little cube. And then as it just sort of adds on, it just gets bigger and bigger. And so this little cube here, given enough room and enough space, these things can get, I'm not joking, if you've ever been out near Trona on the 395, Trona has minerals that sometimes the public can go and collect, and you can collect halite that's like almost too big to fit in like the back of a flatbed truck. I shouldn't say flatbed, like the bed of a truck, like a Tacoma or like an F-150. But they are massively huge, and so it's pretty cool. All right, so the crystallization of minerals. So they need a starting material with atoms that can come together in the proper proportions. And so this is a growth from either a liquid or a gas. So from the gases, they could precipitate out, and from liquids, they do the same thing. The crystals, as they cool, then they cool at different temperatures. So as the material that they're in cools to a different temperature, some minerals start to fall out of solution, some start to form, some stay liquid. And then when it gets to a cooler temperature, more crystals will form, more minerals will fall out of solution. But it needs that medium, if you will. And once again, it needs time and space. So the longer it has, the bigger the crystal can get. The more space it has, the bigger the crystal can get. The less time and space that it has, the smaller they get. But they're still adorable. It's like fun-sized candy bars compared to full-size candy bars. Sure, we love the full-size ones, like there's more of them. But the smaller ones, still delicious, still do their job. And it needs the appropriate temperature and pressure. So these are variables, almost like if you're like cooking. So at certain temperatures, certain minerals will melt. At certain temperatures, some minerals will, or crystals can start to form and fall out of solution. And then also the pressure plays a huge effect. Sometimes the pressure is so great it won't allow for a mineral to crystallize, or sometimes the pressure is so great something that should crystallize won't, and something that shouldn't crystallize will crystallize. And so those are two variables that go along with all of this. And here's some examples. Magma that is cooled below its melting point. So if the magma body, so if we have this big body of magma, right, just this rock mush, this rock soup, as it starts to cool down past its melting point, well, then the minerals start to form, because it's almost like if you ever watch water freeze, you can see like some crystals start to form, even though there's still like some liquid in there, some crystals will start to form. Same thing with the magma. It's cooling down. Some crystals are falling out. Some are still within that mush, but it's starting to solidify. And therefore, if it has a lot of time to solidify and a lot of room, it's going to form some huge crystals. And then we could also have a supersaturated solution, which means that there's more solution or more substances in the solution than it can typically handle. So with that, like it's going to sound weird, but I'm going to use Kool-Aid as an example. If you take Kool-Aid and you put it into like some water, you stir it up, it sort of dissolves away and it's delicious. Well, if you heat up that Kool-Aid, you can put more of the Kool-Aid in there, and then you can stir it up, and then you got like super Kool-Aid. But once it starts to cool, the extra Kool-Aid crystals will reform and fall out to the bottom. And so that's called precipitation. Now, this can also happen if you have like geothermal vents that are blasting like hot steam out. That steam, there's still minerals within that steam. And when it hits like something else, like the side of like a rock wall, it can start to, since it'll cool on there, the minerals will start to form, and you can get these big stalactites. You can get these big, if you look up Mammoth Hot Springs in Yellowstone, you can see these beautiful travertine like cliffs that are made from this same sort of precipitation. And so crystals begin as an initial seed. So they start small and they just keep sort of getting packed on and packed on and packed on. And then as those atoms keep being added, they stick with that 3D structure and just keeps repeating. And then the crystal faces are based on the array of the structure. So quartz, which is a silicon dioxide, so that Si is silicon, the O2 is oxygen. So that silicon dioxide yields quartz. So that silicate structure, and look at this, look at that beautiful little tetrahedra just spinning in infinity out there. Love it. So most of the common rocks in the crust are silicates. These are the most common. So the silicate tetrahedra, which is this guy right here, whoa, no, can combine in several different ways to form many common minerals. So typical cations are, so the cations we don't have to worry about. Essentially, a cation is any positive element or ion. So we got potassium, calcium, sodium, magnesium, aluminum, and iron there. And so all of those form this silicate structure, or the silicate tetrahedra. I actually have a mineral over here that is called tetrahedrite, because it's made out of a bunch of tetrahedra. And this one's really cool. So this right here, I'm going to try and like get a little bit back in the sun. Let's see if we can get it to sparkle. You can't really see it that well back there. I don't know. But anyway, so let me get it closer to. So you can kind of see all these nice little tetrahedras in there. I can't make it spin like it is on the thing, but those are silica tetrahedras. And so one of these minerals is going to be present in here. Now, this is a very heavy one, so it is chock full of iron, chock full of magnesium, some calcium and sodium in there, and it's just like a really cool rock. Like with this one, like so, this one I collected a long time ago out in a mine. But it just has these beautiful, smooth crystal faces. Let me get that. Let me get right up in there so you can really see. You can see how the light sort of plays off of someone. There's like these light coatings of different iron minerals on there. But so that's some of our silicate structure. And with carbonates are an interesting one. So carbonates are minerals that form with this carbonate ion. So the CO3 2-. We're not in chemistry, so I'm not going to worry about it. But that's a very famous polyatomic ion. And so some of our minerals like calcite, it is calcium carbonate. That's CO3, that's a carbonate atom. Dolomite, which some people use in pools and whatnot. It's a calcium magnesium carbonate. So the Ca is calcium, Mg magnesium, CO3 carbonate. There's siderite, which is an iron carbonate, and there's smithsonite, which is a zinc carbonate. But we can see on all of these that carbonate atom attaches itself to a different element, and we get some awesome mineral to form. So these make up many common rocks, including limestone and marble. So limestone, very It used to be used a lot for gravestones, but then as acid rain became a thing, which is from a carbonate, it's water coming through the atmosphere, picking up carbon, and when it landed on those headstones, it became almost like a weak acid and started to eat away at them. But limestone is a great building material. It's been used as a building material through history, and then marble is a very famous like countertop using type material, and also a very very strong rock as well. So continuing on here. So the cool thing with carbonate rocks is that they fizz when you put an acid on them, or effervesce, if we want to take the scientific term. But yeah, so they effervesce, meaning like if you dab a little bit of acid onto a carbonate rock, it'll fizz and you'll start to give off gas, and which is really really neat. And so these are two minerals, so calcite, and then essentially what we'd have here is still another form of calcite, but it's just bound up in these shells of whatever sea creature this is. I don't know. Kraken? Is that a sea creature? I'm joking. These look like clams, mussels, something along those lines. But anyway, so if you were to scratch these up a little bit and put a little bit of acid on them, they would start to fizz and bubble. Now, shouldn't do that with the mussels or clams or whatever they are here. Shouldn't do it with those. Not if they're living anyway. But it's just a cool little thing that you can do. And so this was happening. You would drop a little bit on there, and it starts to fizz and bubble, and it's really, really cool. All right, so this is another one. This is the smithsonite. So this is a zinc oxide. Zinc carbonate, which is really neat. Sort of gives that zinc gives it like that bluish hue, which is like that seafoam greenish look. So which is a cool one. So now we can move to the oxides. And so the oxides, they are compounds of metallic cations, which are positive ions, and oxygen, which makes sense. Oxides, oxygen. And so these are important for many metal ores. Ores may be a word you haven't seen before, but ores just means like it's valuable. Like economically, it's valuable. And so when like mining is going on, whoops, sorry about that. When mining is going on, there's what's called the ore, which is the valuable part, and then the gangue, which is like the leftover scrap stuff. But anyway, so important for many metal ores needed to make things such as iron, chromium, and titanium. So ores are economically useful. They make the money. So gold, that's an ore. Iron, that's an ore. Just because it'll make money, and it's possible to mine. And these are very economically productive mineral deposits. The one right now that's gaining a ton of steam is lithium. So actually, what I'm going to do is I'm going to push my little setup back here. Let me pull this in just because I'm getting into the shades and the shadows, and I don't want the video to look too weird. Anywho, so moving on from there. And so this nice red color is from the oxidation of iron. It's the same thing if you left like an iron nail outside, eventually it's going to rust. This is just rust. That red color, just an iron oxide. That's all it is. And so that's kind of cool. If you're ever out and about and you see this reddish hue or this reddish tint to rocks, you can probably assume that it's iron oxide, rust. And this is hematite. Hematite, so it gets its name, that hema. That's a prefix for stuff usually related to blood. Hematologists study, blood. And so that red color is what gives it the name hematite. Or hematite, however you want to pronounce it. But it is a iron, so we see the Fe, which means iron, and then oxygen, so that's an oxide, so an iron oxide. We don't have to worry about the 2s and the 3s. It's about balancing chemical equations and what's called electronegativity, but we don't have to get into all that. I just like to say it because I'm going to get some use out of that college degree, learning all those fancy words. But anyway, so we'll go to sulfides next. Sulfides are really cool. It's one of my favorite mineral classes. Sulfides, sulfates, and the oxides. That's where it's at. So if you're going to start collecting, go with those ones. Tell them I sent you. No, they'll set you up with some good ones. I'm joking. I don't carry any weights in this town. Anyway, so these are metallic cations. Once again, the positive ion with the sulfide. So the sulfide ion is S2 minus. So anytime we see that S in there, we can pretty much qualify it as a sulfide. So it's important for ores of copper, zinc, nickel, lead, and iron. So if you're familiar with galena, which is lead, you ever picked up lead and it's like, oh my God, it's so heavy. Well, that's a sulfide. It's just a lead sulfide. And then pyrite, which is often called fool's gold, is just an iron sulfide. And so this is one, like, it looks like gold. It has the same shimmer as gold, but it's too light to be gold. It's just a sulfide. It's an imposter, you know? It's just, stay away from it. It's going to lead you down a bad road. No, I'm joking. It's really cool to collect. There's also a version called arsenopyrite, which is like a silver version of fool's gold. And so it's a neat little mineral there. So there's galena. Galena forms these nice little cubes, but boy, oh boy, is this mineral dense. It's just very, very heavy. And then, so here's some of the pyrite that we were talking about. So it looks very much like gold. If you saw this out in the field, you're like, oh my God, I'm rich. I'm never going back to that class and hearing that dude yammer on and say knowledge is delicious. But then you would take it to the metallurgist and they'd be like, no, this is pyrite. And you're like, oh my God, I got to go back and listen to that guy keep talking. So just be aware when you're out there looking for gold. So now we go to sulfates. Sulfates are awesome. So these ones are really cool. They're minerals with the sulfide ion, which is the SO4 2-. And if we can touch on a little bit of chemistry, so if you have SO4, and you combine it with like what's called like a hydrite. So if you make it like into a liquid form, you have sulfuric acid, which is pretty powerful. So this forms gypsum. You can see here this H2O means like when the water sort of binds up with the mineral. It's called a hydrite. But then if you took the water out, it's called an anhydrite. And then it would just be the simply calcium sulfide or sulfate. So CaSO4, calcium sulfate. And this is calcium sulfate with a water molecule attached to it, which is gypsum. So there's gypsum. Pretty cool. We think about this in terms of like the building material and whatnot, but its crystalline structure is amazing. It's gorgeous. There's so much beautiful geometry in nature. Get on out there and get you some. But anyway, so gypsum is really cool because it can, once again, given enough space, given enough time, it can form massively huge crystals. Look at these. Look at these crystals. That's a dude per scale. That's incredible. So this is the Cave of the Crystals. So it's 1,000 feet deep in the silver and lead mine of Nesia. It gets to be 150 degrees in that cave and 100% humidity. I can't remember the exact location of this. I just know it's in South America. But man, 100% humidity. That dude, and you can kind of tell in there, he's kind of like shiny, kind of like greasy looking. It's got to be hotter than heck in there. And he's probably sweating like through his clothes. Poor dude. And so these crystals can get to be 4 feet in diameter, 50 feet in length. So they're just massive. But this is the ultimate testament to enough time and enough space, and you can grow as big as you like. Pretty cool. So when we identify these, we identify them in many different ways. So we go through chemical composition, and this includes having to microprobe things and do what are called wet chemical methods, like what do they dissolve in, what do they crystallize in, like doing different like acid tests. And so it's not always the most efficient. And then we can identify them by crystal structure using what's called an X-ray diffraction machine, which is very expensive and very difficult to operate, and it is radioactive. So it gets to be a little dangerous, and you can't really take that out into the field with you to identify. So instead, we like to use physical properties because they give us clues to sort of narrow all this down. So the physical properties that we use are hardness, how hard the mineral is. That one's kind of self-explanatory. And we sort of use things relative to one another. Can this scratch this? Well, can this scratch that? Can that scratch this? And how one thing can scratch something but not something else gives us a little hierarchy that we'll get to in a second here. So it's called Mohs scale of hardness. So meaning that we start with the softest one and we go up to the hardest one. So this is just a good sort of run through of basic minerals and how hard they are, and then how they compare to common objects. So talc, which is the softest one, if you think of talcum powder, like baby powder or foot powder, if you ground up talc, that's what you get. And you can even know this intuitively, how soft it is. And then we get to gypsum, which we just saw, which has about the hardness of a fingernail. So if you had a sample in your hand, and you're like, I think this might be gypsum, and you go to scratch it, and it won't scratch, not gypsum. It's harder than that. It's got to be something else. Now, if you scratch it and it was able to leave like a scratch on there, you probably have gypsum, but you could also have talc because talc is softer than gypsum, and therefore your fingernail will scratch that too. And then with calcite, fluorite, apatite, orthoclase, quartz, topaz, and corundum, and diamond, they just go on this scale of being 1 through 10. And so with apatite being having sort of the common hardness of a knife blade, if you tried to scratch fluorite with a knife, it better scratch. Otherwise, it's not fluorite, just based off of the softness of it. And so some of these, like you'll see, like geologists carry around like little plates, and sometimes it's glass, sometimes it's like porcelain. But if you had a piece of glass out in the field and you tried to scratch it with like a mineral you found and it doesn't scratch, well, then it can't be anything orthoclase or above. It'd have to be apatite or below. And then, as we go through there, like diamond obviously is our hardest one, but this is a good sort of relative way to put together our hardness scale. And so we have hardness and we also have cleavage. And I know it's kind of like adult terms almost, but no. These are very scientific terms. But cleavage is the tendency of minerals to break along common planar surfaces into geometric shapes that are defined by their crystal structure. So kind of like if I had one of those cubes of salt and I broke it and I smashed it, it would break into other little cubes. That's how it cleaves. If you've seen biotite, so biotite, or even like a muscovite, which is a mica, any of those micas that are like flat sheets, you can sort of rip those apart in little flat planes, and it's going to be sort of that same looking structure over and over again. So that's the cleavage of it. And here's the perfect example. So that mica, as it flakes off in those sheets. So that is a form of cleavage. It cleaves off in these perfect little sheets. And there's the cleavage in calcite. As it's broken up, it may not be perfect. Some pieces are going to fly off, but it breaks up into these little cubic structures. I'm pointing at the screen as if you can see me pointing at the screen, but it breaks up in these little cubic structures. And there's halite, that table salt I was telling you about. Yeah, if you look at them under a microscope, you're going to see it's a bunch of little cubes. Delicious little cubes. Anyway, so after cleavage, we also look at fracture. So how does it fracture? And this is the tendency to break along other surfaces. So not those perfect little planes, but other surfaces. So basalt has this conchoidal fracture. So it's almost like this circular fracture. It looks like a bottle. But that's just the way that it fractures. And so I have down here, which is called botryoidal hematite. So it's that kind of that rock we saw before. So I'm going to put up to the camera here. I hope I don't drop it and smash my laptop. You can see it's kind of like bubbly. And so this one, if you broke it apart, would have that conchoidal fracture. And it's just another way that things sort of break apart. So if it doesn't have cleavage, it has fracture. And then we have a couple other things. So color. It's kind of a poor indicator, but it can help because as we've seen, like something may look gold, but it's not gold. We also have specific gravity, like how heavy and dense it is, and then the crystal shape. Sometimes those can be indicative. So now if we look at rocks. So rocks are just an aggregate of one or more minerals or a body of undifferentiated mineral matter. If you think of like obsidian, like the one we just saw, like with that conchoidal fracture, that one, it's just like, it looks like one thing the whole way through. And so that's what we would have there. It's not, more than one mineral. It's just undifferentiated mineral matter. Or it could be of solid organic matter. Coal is this other one, which we talked about before. So there's no more than one crystal. No more than one crystal. There's more than one crystal within the rock. It could also be volcanic glass, which is obsidian, solidified organic matter, which is the coal. So the appearance is controlled by the composition and the size of the arrangement of the aggregate grains. Jeez, oh, Pete. So once again, more time, more space, you can get bigger grains, better texture, and that's sort of one of the things that like defines a certain classification of rocks. So we mainly have 3 different types of rocks. We're going to get much more into these next week. But we have igneous. So igneous taking the form of ignite. These are all rocks that are born of fire. So they form by the solidification of molten rock, which is magma. Now magma, so when we think of magma, that's when it's below the surface. Once it erupts, that was a weird eruption, but once it does that and then cools on the surface or is on the surface, it is then the lava. So magma in the earth, lava on the top. And then we have sedimentary, which is a bunch of broken down pieces of other rocks that have sort of been smooshed together, compacted, cemented, and they do what's called lithification, which is becoming a rock. And so it's just a bunch of the sand, silts, clays, and shells being compacted, heated up, and then we have rocks, or a sedimentary rock. And then metamorphic can be either one of the rocks above, but what happens is it gets buried, it gets heated, and it gets pressurized to the point where it transforms itself. So it metamorphoses into another rock. Let's look at some of them. All right, so igneous rocks, we have two types. There's intrusive and extrusive. Intrusive, so I'm going to go kind of quick through this just because we're going to spend more time on it next week. But intrusive rocks cool within the earth. Extrusive rocks cool outside of the earth. So extrusive, usually like your volcanic eruptions. And then intrusive is if that magma never makes its way to the surface and it cools down below, eventually uplift will expose it. And we have ourselves an intrusive igneous rock. All right, so plutonic. Plutonic means it forms within the earth. Pluto was the god of the underworld. That's where you get that term from. So these are slow cooling rocks. They get big, interlocking, large crystals. And a great example of that is granite. So here's our common granite. It's an igneous intrusive rock. We can see, the different colors in there. If we had a sample in front of our face, you can see it better. But these really nice orderly crystals that have formed and then in an aggregate make up granite. So in there you have feldspars, you have quartz, you have amphibole, you have hornblende, all these different types of minerals that make up our granites. Now, extrusive rocks are volcanic rocks. So Vulcan, who's a god of something, god of fire, I think, right? So they form on the surface of the earth as a result of the volcanic eruptions. So rapid cooling. So these cool quick. They're going from within the earth where it's super hot, super pressurized. They get extruded like that in a volcanic eruption. And then they're coming up to the surface of the earth, which is much cooler relative to down below. So they cool quick, which means we get little tiny grains in crystals. And so we can get glassy or fine grain. Glassy being like obsidian, fine grain to being like a basalt. Hey, look at that. There's an example of it. So there's basalt. So those are two types. This ropey stuff is called pahoehoe lava. It's very ropey, very flowy. And then there's also this like sharp cinder-like lava, and this is called supposedly, I don't know 100%, but it was named because walking on it, you'd be like, my foot's getting torn to hell because of all this material. And that's why shoes were invented. But these ones, you'd be walking along, it'd be like, oh, pahoehoe, this is easy. I don't say pahoehoe for that. I'm sure that has a meaning. Just this ropey, smooth-looking lava as opposed to the sharp lava. Lava, I like it. So here's a little compare and contrast between our igneous rocks with intrusive and extrusive. So here's our granite, and you can see bigger mineral grains. This cooled within the earth, and that's our granite. It's our intrusive igneous rock. Same as up here. Bigger crystals, you can see them in here. It's a little harder to pick out. Those are bigger crystal grains, making it an intrusive igneous rock, as compared to these ones, which are extrusive. And you can see these tiny, tiny little mineral grains. They're just as important. They're just as beautiful. All these rocks are gorgeous. They're just different. Bigger mineral grains, tiny mineral grains, all serve their purpose. All amazing little feats of science. Sort of solidified magma. It's just really, really cool to see. Now, sedimentary rocks. So you think of the Grand Canyon. Grand Canyon is just full of sedimentary rocks. All of these are just rock layers piled on top of one another. It's a gorgeous place to be. So the origin of the sediment. So sedimentary rocks are just little pieces of broken down other rocks. And so where those other rocks come from, the origin of the sediment, if you will, I'm going to move things back a little bit. That sun keeps creeping up on me, and I'm just going to keep moving forward. I'm like Dracula, just trying to stay out of the light here. Anywho, so it's produced by the weathering and erosion, or the precipitation from a solution. We're only going to really look at the weathering and the erosion part. But so as other rocks are sort of broken down and put into like bits and then transformed and deposited, after a while, they're going to form a sedimentary rock. And so this weathering is just the chemical and the mechanical breakdown of rocks. Sometimes like the chemicals will deteriorate or deteriorate the rock and it'll break down. Sometimes like if there's like a rock fall, like a big rock will get smashed into a bunch of little rocks. And so that's the mechanical breakdown. And then the erosion is the process of moving it along, taking it from one place to another so it can be deposited and then left to form a rock. So sediment types. So there are clastic sediments. These are sediments that are derived from the physical deposition of particles produced by the weathering and erosion of pre-existing rocks. So clastic is just like a clast. It's a piece of it. And then there's chemical and biochemical sediments. that are precipitated from solution. So whether it be from like hot geothermal gases or from some other biogeochemical process, like making of shells and then the burial and compaction of shells. So that's another way that these can form. And so the clastic ones you can see here are just like little pieces of rocks. These are all former bigger rocks, and they just come together as little clasts, as opposed to the biogeochemical ones. I shouldn't say biogeochemical, just chemical and biochemical, to where it's more of like a soupy matrix with maybe like shells in there, organic material, chemical precipitation type stuff. Whoa, I didn't mean to do that. So anyway, hopping on back to it. Lithification. All right, let's go there. So the process that converts sediments into solid rock. So this is what happens here. So in sedimentary rocks, they all get piled up, and then they go through lithification, which is essentially heat and pressure and cement coming together. Whomp, we got ourselves a sedimentary rock. So we need to be compacted. That's the first thing. All these layers need to stack up and become compacted. They need to be cemented. So the cementation means like there's like different like chemical cements, biological cements that will lock all these grains together. And so we can see here, this is a thin section, which is a rock cut super thin. And we have these mineral grains within it. And then this material in between, that's the cement. So it could be biological material. It could be like broken down chemical material from the rocks, but it's just the cement that holds it together. Now, so here's the whole process. So we got weathering and erosion, transportation, deposition, and then it gets buried, it gets lithified, it gets heated, and a beautiful sedimentary rock is born. Circle of life. I'm gonna do a little Lion King thing. Even though this is just a quartz crystal, it's not a lion and it's not a sedimentary rock, so I can't keep going with that bit in good conscience. Now we get to metamorphic rocks, which are really cool. These are just stressed out rocks, man. They have seen some things in their life, and so it's just any of our other types of rocks. It could be igneous, it could be sedimentary, and what happens? It just gets heated and pressurized. And when you put enough heat and pressure on things, they change. They change. And so we have two different types. We could think of like regional metamorphism, which is like if an area is being like pushed together, which we'll get to with plate tectonics, you can get like these big metamorphic changes over a huge area. Or you can have what's called contact metamorphism, which means that if you have like a magma body, that heat is going to alter the surrounding rock around it just by like partially melting it, and then it'll solidify again, but it alters the rock. And so we have a couple different rocks here. So we have a conglomerate, which is we saw like those clastic sediments. So those clastic sediments being cemented will form us a conglomerate. And then when it gets metamorphosed, it looks like this. It's just been sort of smeared across like it's cream cheese on a bagel there. But don't eat it. You will be missing some teeth. And then it becomes a metaconglomerate. So a conglomerate that's been metamorphosed. And so we have our granite, our nice, beautiful, intrusive plutonic rock granite. And then we're going to heat it. We're going to pressurize it. We're going to put it through 2020. And it's just going to come out a completely different thing. Oddly enough, and let me move my big goofy head here, it's called gneiss. Gneiss, gneiss. So this is our gneiss right there. So once again, just it's seen some things. It's been heated, smeared, like pulled, and then it re-solidifies. And some of these mineral grains line up. You can see like in the top one, they're kind of like the black grains are like sparsed across. In the bottom one, they're almost like flowing, like it looks like a river. But that's the process of metamorphism. And so once again, here's like a thin section of it. And then when it gets metamorphosed, it kind of like lines up with its homies. Like it goes with the people that it partially melted with to create these sort of more congruous and continuous flows of metamorphic rocks. And this is just a gross looking rock. Look at that. Gross. Yuck. No, thank you. Anyway, let's hop away from there. But anyway, these are just, so limestone turns into marble, and then marble quarries, and then sculptors can make some beautiful, beautiful statues. So take a moment. Look at this rock cycle. I'm going to not jibber jabber for 1 second. I'm going to let you go on and look at that. Okay, cool. Told you it was only 1 second. But so the rock cycle, this is how everything flows in and of itself. So we could take, let's start down here in the bottom left. So we have magma, either the magma solidifies or it comes to the surface and solidifies. And then we get igneous rock, whether it be on top or down below. And then this will be uplifted, and these exposed rocks get broken down, turned into sediments, which make their way through, and you get burial and compaction. And then after you get that sedimentary rock, maybe it gets exposed, and it gets heated and pressurized, and it becomes a metamorphic. And then it can melt again, and that whole cycle can go through. Or these igneous rocks can get heated and pressurized, and they become metamorphic. Or these sedimentary rocks, once they form and they become metamorphic, they can be broken down again into sediments and almost like go on this same cycle. So this is the beauty of the rock cycle, is that any rock that we have can become any other rock just by going through these motions. And so take some time and look at that. You can always come back to this lecture or just to the regular PowerPoint to take a peek, but this will be incredibly helpful on your adaptive practice and your quiz. And so essentially it kind of looks like this. Igneous is the parent rock, and we can go on any pathway from there. Igneous can go to metamorphic. Igneous can go, it can be uplifted, weathered, and eroded and become sedimentary. Sedimentary can melt, become magma, and go back to igneous rocks. Metamorphic rocks can melt and go back to igneous. They can be broken apart and go back to sedimentary. And that's the thing we need to respect about the rock cycle and appreciate about it. It shows us that through these various pathways, we can take one rock and make it into another. So there you go, once again, in the flesh. And we can kind of see here, these are the planes that would flow through towards the deposition, just kind of like some generalized. And so this is like an evaporite bed. And so they'll flood these areas with water, let the heat evaporate the water off. And then usually there's salt left over. Halite has precipitated from the solution. Now, and then of course there's magmatism, which would bring mantle material to the top, solidify, and go through that rock cycle. And then here's the uplift. Whatever cooled down below can then be uplifted. We'll go over this much more next week, but I just want to introduce it. All right. We're not going to worry about divergent boundaries. We're going to get into that in a couple of weeks. But these are a couple of the questions you're going to see on your quiz, not the adaptive practice, but your quiz. And so one of them says, which rock type can be made into a metamorphic rock? We just saw from the rock cycle, all of them. So when it says check all that apply, every single rock can be made into a metamorphic rock. Even metamorphic rocks can. If it gets metamorphosed and then it's on the surface and then it gets buried and heated and pressurized again, metamorphic rocks can re-metamorphose. And so this one, it would be every single one of them. Click all of them, hit check it, and you're good to go. Which of the following types of rock is organic and therefore cannot be made of minerals? So organic rocks, remember that has to be like plant material or like shells of like marine life. So that is our coal. And so I'm trying to think of like the best way to put it here. Coal just being made up of organic material. And we had said that minerals are non-organic. So therefore we have coal. And then lastly, sedimentary rocks may form into a chemical precipitate that is left after the evaporation of a liquid. That was what we just saw. I'm going to hop back to that picture. That's an evaporite bed. So all that water will evaporate, and then we just have material left over that's been precipitated. So sedimentary rocks may form from a chemical precipitate that is left after the evaporation of the liquid. Absolutely. Once the liquid's gone, you could have a sedimentary rock line over. So there you go. That's our lecture. We are all done. Thank you for joining me. Get on that CK12. Ask questions if you got them, but get on it. Otherwise, I will talk to you later on. Thank you for joining me.